Feature recognition is the process by which a computer evaluates the correspondence between several images. This process is used in many computer vision systems, such as facial recognition, text recognition, image mosaics, and image stitching. In this video, we will be looking into its use in image stitching in the case of panoramic images. Looking at a basic example, we have two images. For simplification purposes, we have images of equal size with relatively consistent angle and lighting. These are successive images of the same scene with a small area of overlap. We want to computationally identify these areas of overlap in order to match the images together. Qualitatively, we can see that the area within the red box overlaps for these two images. Identifying these points is the most mathematically intensive part of this process. Once the points are identified, we match up these corresponding points and stitch the image together to create a panoramic image of the scene. In order to find matching points between separate images, we find areas of similarity in the different images. This is done by a process called Harris corner detection. In order to find unique points of correspondence, we look for small areas of great variation within the image. Different parts of the image can be categorized as flat regions, edges, or corners. Flat regions are parts of the image with little change when moved in any direction. These are usually an area of consistent color, such as the wall of a building or an expansive sky. Edges have some change when moved in certain directions, but no change when moved along the edge. This could be a segment, such as the side of a building, where moving side to side produces large amounts of change, while sliding the region up or down the building creates a relatively similar image. Finally, the most useful kinds of regions, the ones that we will be using to detect similar spots in images, are corners. These are regions in which there is a great amount of change when moved in any direction. Because these points are relatively unique, we can use them to find correspondence between the two images. We want to find the areas with the greatest amount of change when moved in any direction, the corners. We can do this through mathematical feature detection. Consider the small square region W of the image L being shifted by U, V. We evaluate how each pixel of W changes using a sum of square differences, SSD, equation, defined as the error, E, of U, V. In this case, I is the intensity of change moving in the x direction, a distance U, and in the y direction, a distance V. The equation is taking the sum of all of these changes and computing an error factor from it. Taking a Taylor series first-order approximation of I, we now have the equation shown. This allows us to rewrite the error E of U, V as the equation shown, which we can simplify to the equation shown, and once more to the equation shown. We will take this matrix within the parentheses to be H. To find the directional movements that will result in the largest or smallest E values, which we can use to map these unique points to overlaps in other images, we use the eigenvalues of H. We solve for the eigenvalues of H. We can now use this information to determine which directions have largest or smallest E values and the magnitude of such changes. Relating this back to the different classifications of area, flat region, edge, or corner, areas with small lambda plus and lambda minus values are flat regions. Regions in which lambda plus is significantly larger than lambda minus are edges. And areas in which lambda plus and lambda minus are both large are corners where E increases in all directions. As an example of the feature detection process, we can look at a simplified I gradient of black and white squares. To get this, we took the gradient at each point in the image and created the H matrix from all these entries. The corresponding eigenvalue grids for this area of the image would look like this. We then computed the eigenvalues and found the points where lambda minus was a local maxima and tracked these as feature points. We used such feature points to match up the two images. We have implemented the Harris corner detection in MATLAB. This program takes in an image and denotes the regions of greatest variance. Here are a few examples. In summary, this method of feature detection involves transforming the image into a grid of small areas with grayscale pixel values. These values are then analyzed by determining eigenvalues of translation and using this to find the areas with greatest change that can be that can be described as corners. These corners help to denote feature points that can be used to overlay the two images. This method still holds for rotated images because the eigenvalues themselves will remain the same. However, this method of feature detection fails to account for scaled images, as doing so would change the eigenvalue, making the image unable to correlate.